Hello everyone. Today I'm going to solve an IMO number theory problem. So the question is, suppose that for A and B natural numbers, the following quotient is an integer. Prove that Q is a square number. In other words, there exists K such that Q is K squared and K is an integer. So this is from IMO 988 and it was problem 6. Okay. So let's look at the question. It's giving us a quotient a squared plus b squared divided by 1 plus ab, where a and b are natural numbers. And we want to actually prove that q is equal to k squared for some k natural number. Okay, so let's take a look at this this quotient we have here, a squared plus b squared divided by 1 plus ab. The first step approximate q. So why that seems to be a reasonable decision. If you look at this quotient here, a squared plus b squared divided by 1 plus ab, you see that a and b are natural numbers. So assuming that this is a large number, if I just get rid of 1, I should probably get a good approximation of q, right? So observe that q should be approximately equal to this quotient. And if you simplify it, you get to this sum, a divided by b plus b divided by a. And right off the bat, let us just assume that without loss of generality, I can assume that a is less than or equal b. Okay, so now what? Now, since q is an integer, it's a natural number, I'm going to make the following guess. Q is between b divided by a and 1 plus b divided by a. Okay, so let's prove it. Right hand side is the easiest. Why? Because we just basically showed it. Q is a squared plus b squared divided by 1 plus ab. And if I reduce the denominator, I get something larger. So I have ab, and this is a plus a divided by b plus b divided by a. And we just showed that we just assumed that b is at least a. So I should get that this is less than or equal to 1 plus divided a, and so because we have a strict inequality here, we get the right hand side, right? So the right hand side is done. Now what about the left hand side? Left hand side is we want to show that b divided by a is at most q. To see this, denote c equal to b minus qa. So we basically want to show that c is the question is c is non-positive. Because c is a natural numbers, so if not, since as c is a natural number, c must be at least equal to 1, right? Now let us just do some basic manipulation. I have a squared plus b squared is equal to q1 plus ab, and this is q plus qab, and from here I can see that q is equal to a squared plus b q, this is b minus qa, and this is equal to a squared plus bc, and this is equal to a squared plus qa plus c times c. I just replace b with qa plus c, and this is equal to a squared plus qac plus c squared. Now we get the contradiction, right? The reason is the right hand side here has a positive term, q is positive, a is positive, and c is larger than 1, is larger than 0, and so this side is larger than q, and that's the contradiction, right? So, but this is larger than q, and this gives us a contradiction. So we basically showed the left hand side as well. So the left hand side is also correct. Okay? So what next? So we basically showed that q lies between these two values, which are like fall apart by 1. So let me just rewrite something here. I'm going to move here. I'm going to move to here, and I'm going to write this as b divided by a is at most q, and this is less than 1 plus b divided by a, and therefore if I let b equal to qa minus r, I get that r is at least 0 and is less than 1. And so this is what we actually showed. This comes from, we first approximated q. We made a guess by just a simple idea here, and then we get this bound for q, and then we just rewrite it, and we arrive at this simple equation. So okay, this was the first part. The second step is to look at this. Okay, how am I going to use the first step? The second step. Note that this equation that I have here is basically quadratic, right? Is basically quadratic. Okay, let me write this, and this, let me just make a definition here. G of xy is equal to x squared plus y squared divided by 1 plus x. And I know that g of a and b is equal to q. Okay, so this is basically the same as saying x squared plus y squared minus qxy is 0. And this is the same as saying that x squared minus qy times x plus y squared minus q is 0. And this is a quadratic equation, right? I know, for example, that g of ab is 0, and from here I basically get what? I basically get b squared minus qy times b plus a squared minus q is 0. And so if I fix a, and basically let f of x to be x squared minus q, sorry, here instead of phi I should have qa, and so I have x squared minus qa times b plus a squared minus q is 0. And here, oops, another mistake. Should remove b, I should put x here. And so if I let this to be the definition, then I get that f of b is 0. But this is a quadratic equation, so let another root, let the other root be b prime, then what would happen? Then basically the sum of roots, b prime plus b, because b was a root, right? b prime plus b must be equal to qa. Just the sum of basically what I did here. This is x minus b prime, and if you expand it, you get prime x plus b prime, and so we have b plus b prime equal to qa. Alright, and from here I get that b prime is qa minus b, and this is exactly the value r that we had there, right? And so basically b prime is equal to r, and therefore f of r is 0, but we know that r is strictly less than a and is non-negative. Sounds great. So from here, basically what we understand is r squared plus p squared divided on 1 plus rp is equal to q, right? Because we just what we need to do is just from here go back and replace f of r equal to 0, and then from here we basically go back all the way to get to this equation that we had, right? Let me actually write it for you. So f of r is equal to 0 basically means r squared minus qa r plus a squared minus q is equal to 0. Oops, now I just found a mistake here, sorry again. This is a squared, this is ra, and then I just need to rewrite this as r squared plus a squared is equal to q plus qar, and this is q times 1 plus ar, and here I just get that q is r squared plus a squared divided by 1 plus ar. Awesome. Okay, so what happened? We started with, let me just draw a line here and start over. Start here, step 3, step 3. Notice that I started with a and b. I said, okay, a squared plus b squared divided by 1 plus ab is equal to q, and then found r such that r is non-negative and strictly less than a, such that r squared plus a squared divided by 1 plus ra is equal to q. And here I also made the assumption that a is less than or equal to b. Okay, so we started with a pair AB, and then from here we get a pair RA, such that R is strictly less than A and it's non-negative. And then we can continue this process, right? And because R is supposed to be non-negative, R is non-negative here, this process has to stop, right? So I'm gonna get somewhere like 0, like some, let's say, k, such that 0 to the power 2 k squared divided by 1 plus 0 times k is q, and this basically means that q is k squared, and that completes the proof. Thank you so much for watching. Don't forget to subscribe to my channel for more fun problem solvings. Thank you.